Hello, I am Ehsan Jafari, an expert in membrane technology. Before we start learning this lecture, just a quick note. I am available for your private consulting, system design, troubleshooting, and procurement. If you need professional support for your business, just hit me up on WhatsApp. Now let's begin the tutorial.
In the second step, for the selection of a membrane, you learn how to select a suitable material for the process. You learn about the selection factors, types of materials and structures, advantage and disadvantage, some properties, classification based on the process, and etc. Now the third step is decision on the module type. In this part, I will describe the types of membrane modules in detail. Decision on membrane module. The ideal module ensures the following aspects: good and constant flow over the membranes without dead water zones, low pressure losses, high packing density, low cost production, easy cleaning, easy replacement of the membranes, and low disposition for clogging. Membrane forms and modules. Industrial membrane plants often require hundreds to thousands of square meters of the membrane to perform the separation required on a useful scale. Before a membrane separation can be performed industrially, therefore, methods of economically and efficiently packaging large areas of membrane are required. These packages are called membrane modules. Depending on the manufacturing process, we distinguish two basic membrane forms: tubular membranes and flat membranes. These membranes are arranged in an engineered unit, the module. Besides the membrane itself, the module is of decisive importance for the efficiency of a membrane stage. There are a huge number of different module constructions because the modules are adapted in their construction to meet the requirements of the end use. The basic membrane forms, which depends on the conditions of production, are assigned to the module forms represented in the table. The basic membrane forms, which depend on the condition of production, are assigned to the module forms represented in the table. In some special cases, the strict allocation is not permissible if some membranes used in tube modules were manufactured by the tubular processing of flat membranes. Concerning tubular membranes, we distinguish as module constructions the tube, capillary, and hollow fiber module. For flat membranes, we distinguish plate, spiral-wound, cushion, and disc tube modules. The different module forms can be characterized regarding the arrangement of the separation layer, the component density, and with the tubular diaphragms regarding the diameter. Due to the different characteristics related to performance and operation, such as operating mode, susceptibility to blockage, simple backwashing, and etc., and the surface-specific module cost, certain module types are preferentially used depending on the water and wastewater to be treated. Now, let's have a look at the characteristics, advantage, and disadvantage of tubular membranes. In this group, the tube module has the lowest packing density, which is the main disadvantage for this module. The arrangement of the separation layer is inside with the largest diameter and cross-flow operating mode. Some of the advantages, such as hardly susceptible to blockage, and low pressure loss operation controlled by covering layer is possible. The most commonly used membrane module for municipal water treatment is the Hallow-fiber, with the highest component density and lowest diameter in this form, and also dead-end operating mode. The main disadvantage is susceptible to blockage pressure loss, but high pressure resistance and being affordable are some of the benefits of this module. In the selection of a module, cost, always important, is difficult to quantify because the actual selling price of the same module design varies widely depending on the application. Generally, high pressure modules are more expensive than low pressure or vacuum modules. The total volume of product likely to be produced to satisfy a particular application is a key issue. For example, Spirel-wound modules for reverse osmosis are produced by 3 or 4 manufacturers in large volumes, resulting in severe competition and low prices. Similar modules used in ultrafiltration are produced in much lower numbers and so are much more expensive. Hollow fiber modules are significantly cheaper per square meter of the membrane than spiral-wound or plate and frame modules, but they can only be economically produced for very high volume applications that justify the expense of developing and building the spinning and module fabrication equipment. This cost advantage is often offset by the lower fluxes of the membranes compared with their flat-sheet equivalents. Now I'm going to explain these modules in detail. Plate and frame modules. Plate and frame modules were one of the earliest types of the membrane system. These modules provide good flow control on both the permeate and feed side of the membrane, but a large number of spacer plates and seals lead to high module cost. Membrane, feed spacers, and product spacers are layered together between two end plates. The feed mixture is forced across the surface of the membrane. Permeate enters the membrane envelope, enters the permeate channel, and is collected through the central permeate connection channel. Low packing density is one of major problems for plate and frame membrane systems. Low efficiency compared to other configurations and high pressure drop are other problems that plague plate and frame systems as well. Irreversible damage is also a common problem because of the constant build-up on the membrane surface. In addition, plate and frames are difficult and expensive to clean and maintain. Entire rocks must be disassembled for replacement, and the cost per square meter can be very high. A couple main advantages of plate and frame membrane systems include solids being able to be easily separated from water and easy removal or cleaning of filter surfaces. Certain cross-flow plate and frame systems allow the plate and frame to be rotated, allowing more shearing forces and fouling reduction. Tubular modules. Tubular membrane modules are tube-like structures with porous walls. Tubular modules work through tangential crossflow and are generally used to process difficult feed streams such as those with high dissolved solids, high suspended solids, and or oil, grease, or fats. They typically have 1/2 to 1 inch outside diameter tubes that are packed individually into a long PVC housing and can be either polymer or ceramic based. How it works. Tubular modules consist of a minimum of two tubes, the inner tube called the membrane tube and the outer tube, which is the shell. The feed stream goes across the length of the membrane tube and is filtered out into the outer shell while concentrate collects at the opposite end of the membrane tube. They are commonly used for applications such as oily wastewater treatment, membrane bioreactor, and other high solids processes. Some disadvantages. Low packing density and large size are disadvantages of tubular modules. The packing density of tubular modules is higher than plate and frame systems, but lower than capillary, hollow fiber, and spiral-wound elements. Because of the large inner diameter of tubular modules, flow requirements are higher than those of other system configurations. The capital and operating costs for tubular membranes tend to be very high, along with the requirements for large footprints for capital equipment. Some advantages of this module. Tubular systems have less fouling compared to plate and frame systems, and a similar amount of fouling when compared to spiral and capillary. Tubular systems allow for robust cleaning methods such as the use of harsh chemicals, backwash, and even mechanical cleaning, which might not be available for other system configurations. They can handle the highest solids and emulsified oil load compared to many other membrane types and can be physically cleaned with sponge bowls. Hollow fiber modules. Hollow fiber filtration utilizes thousands of long, porous filaments ranging from 1 to 3.5 millimeters wide that are put in place in a PVC shell. Each filament is very narrow in diameter and flexible. Hollow fiber can find uses for gas separation, reverse osmosis, and ultrafiltration applications. How it works? Hollow fiber filtration works on the same principle as tubular and capillary configurations, but utilizes a small tube diameter which allows for flexibility. Common applications for hollow fiber membranes include membrane bioreactor, reverse osmosis pretreatment, industrial water and wastewater, juice processing, and biotech applications. Because the fiber wall must support considerable hydrostatic pressure, the fiber usually have small diameters and thick walls, typically 50 micrometers internal diameter and 100 to 200 micrometers outer diameter. Hollow fiber membrane modules are formed in two basic geometries as you can see in this figure, shell side and bore side feed modules. Shell side feed modules are generally used for high pressure applications up to 70 bar. The flow regime is from outside of the fiber or shell side through the pores in the membrane wall to the lumen side. Fouling on the feed side of the membrane can be a problem with this design, and pretreatment of the feed stream to remove particulates is required. Bore-side feed modules are generally used for medium pressure feed stream up to 10 bar, for which good flow control to minimize fouling and concentration polarization on the feed side of the membrane. The main difference between hollow fiber and tubular membranes is the flow regime that can be achieved on the bore side. In hollow fiber that the internal diameter is less than 1 millimeter, only laminar flow can be achieved and therefore mixing at the membrane surface is limited. Under these conditions, external concentration polarization, fouling, and scaling can reduce mass transport across the membrane. In tubular membranes that internal diameter is larger than 2 millimeters, turbulence can be easily achieved and concentration polarization and fouling as well as scaling can be reduced. Some disadvantages of hollow fiber modules. Irreversible fouling and fiber breakage are the main problems concerning hollow fiber filtration. Because of the flexibility of the fibers, they are more likely to break when under high strain compared to other methods of filtration such as tubular or spiral-wound elements. Hollow fiber membranes tend to have moderate capital cost but high operating cost compared to the other configurations. If I want to tell you some advantages of this module, hollow fiber membranes feature a very high packing density because of the small strand diameter. Because of the flexibility of the strands, certain filter configurations are possible that cannot be achieved in other filtration configurations. They can also be backflushed from the permeate side and can process feed streams with high total suspended solids. Spiral wound modules. Spiral wound modules consist of membranes, feed spacers, permeate spacers, and a permeate tube. As you can see in this animation, first a membrane is laid out and folded in half with membrane facing inward. The feed spacer is then put in between the folded membranes, forming a membrane sandwich. The purpose of the feed spacer is to provide a space for water to flow between the membrane surfaces and to allow for uniform flow between the membrane leaves. Next, the permeate spacer is attached to the permeate tube and the membrane sandwich prepared earlier is attached to the permeate spacer using glue. The next permeate layer is laid down and sealed with glue and the whole process is repeated until all of the required permeate spacers have been attached to the membranes. The finished membrane layers then are wrapped around the tube creating the spiral shape. Spiral wound elements can be used for a variety of different applications including desalination applications, dye dissolving and concentration, sulfate removal, oil separation in wastewater applications, whey protein concentration, lactose concentration, and cathodic or anodic paint recovery, among many others. How it works. As I have already mentioned at the first of this section, feed travels through the flow channels tangentially across the length of the element. Filtrate smaller than the molecular weight cutoff will then pass across the membrane surface into the permeate spacer, where it is carried down the permeate spacer towards the permeate tube. The remainder of the feed then becomes concentrated at the end of the element body. Some disadvantages. Spiral element fouling is greater than fouling in tubular filtration processes. Due to the high packing density, total suspended solids must be reduced to a minimum less than 5 mg per liter in the feed stream to prevent plugging of the membrane. Spiral elements also cannot handle mechanical cleaning like tubular elements and contain lower packing density than hollow fiber. Some advantages. Spiral wound elements come in multiple configurations with different spacers, membrane types, lengths, and diameters that allow to be used in a wide variety of applications. These elements have a very high packing density surpassing the packing density of plate and frame, tubular, and capillary configurations. Spiral membranes also allow for easy cleaning through cleaning in place. Additionally, spiral-wound elements offer the best value per membrane area, smallest footprint, robust design which prevent membrane breakage compared to hollow fiber and has relatively low capital and operating costs.